So, last class we did Lewis structures again, correct?
Yep.
And I guess everyone is pretty comfortable doing Lewis structures. So we have seen already in the lab that some of the molecules, when you make Lewis structures, more than one possible structure, you could draw more than one possible structure, right? So, as it says, there are some molecules which has more than one possible Lewis structure, and the single Lewis structure when we draw on paper, that actually does not tell us the complete picture of the molecule. We are talking about only molecule who has more than one Lewis structure, okay? If a molecule has only one possible structure, then that's it. There is nothing, no mystery behind it. But if there is a molecule with more than one possible Lewis structure, you might be wondering, so actually the molecule will be like what? Right? Which structure is the molecule is going to have in reality? So in reality, the molecule is going to be kind of a blend of all those possible structures.
So you can have an octet on an octet on an octet stack.
Uh-huh. You can have a lot of things like that. Let's look at this example, SO2 molecule. Of course, this Lewis structure, since, as I said, they do everything with the dots, so it may not be clear. So I'm just going to draw the structures as you know on the side. Okay. Whoa. OSO, and in the left side, this sulfur is double bonded. One pair, 1, 2, 3, 4, 5, 6. Okay, this is the left side picture, and in the right side picture, this O is double bonded. Okay, so these are the two possible Lewis structures you can come up with for SO2 molecule, right? So, as I said, if you go and take an actual sample of SO2 molecule and if you analyze it, it's not going to be like some molecules are like this and then some molecules are like this. It's not the case. In reality, the molecule is going to be a blend of these two, or in other words, well, these two bonds are different. One is a double bond between oxygen and sulfur, and one is a single bond between oxygen and sulfur, right? So definitely the strength of a double bond is different from a single bond. The length of a double bond is different from a single bond. But as I said, if you look at the real molecule, you are not going to see any of those differences. These two bonds are going to be with the same length, with the same character, which is kind of a partial double bond. It is not a complete double bond, it is not a complete single bond, but a partial double bond character. That's what in reality the molecule will be like.
When you said there could be a different length, you were emphasizing the word length.
Mm-hmm.
So there can be a different length.
Yes, we are not going to learn about bond lengths, but double bonds, single bond, double bond, triple bond, those three bonds have different lengths. They are not the same. When we draw, we just draw a line. We are not going to worry about, but they have three different lengths. And we are not going to learn the bond length details, so don't worry about that. What you have to remember is, as I said, those two bonds, in reality, they are not going to be feeling different. They are going to be exactly the same. So this phenomenon of molecules having different possible structures and existing as a blend of those different structures is called resonance. Not all the molecules have resonance. Only molecules who you can have more than one possible Lewis structure can have resonance. So here is an example, like you are looking at a pair of photographs. These are, as you can see, a shell, and each photograph is the other sides of a shell, right? If you look at only one photograph, it doesn't give you the complete picture of the shell. Say for example, if you look at the top photograph, you don't know how the other side of the shell is, correct? If you look only at the bottom photograph, you don't know how the other side of the shell is. But when you see both together, you immediately get it, right? You can visualize in your head how the shell is going to be in 3-dimensional? Same thing. We have two different Lewis structures. Each structure will give you some aspect of that molecule, but not the complete picture. But when you see all those structures together, you can imagine in 3-dimension how the molecule is going to be. The molecule is going to be a blend of whatever structures you are seeing. So that is resonance. So in other words, here is the resonance pictures of a shell. So we are going to check how do we write resonance structures. So here is a molecule N2O, and if anyone is wondering which one will go in the middle, if you look at the electronegativities, nitrogen has less electronegativity than oxygen. That is why the atom arrangement is going to be one nitrogen in the middle and then one nitrogen and oxygen on either side. So first thing is we start writing our Lewis structures, because resonance structures are nothing but various Lewis structures, right? So we have to come up with the all possible Lewis structures of N2O. So let's start with the first one. So this is the atom arrangement. How many valence electrons we have in N2O? Nitrogen is in group 5, 2 of them, so 10, and oxygen is in group 6, so total we have 16 valence electrons. Okay, so we connect them with a single bond. So we have used 4 electrons. We have to put another 12 electrons in the picture, right? How do we arrange them satisfying everyone's octet? Well, we will go by procedure. We will start with outermost ones. So oxygen can take 6 more. So we have another 6 which we will put right here. But of course that doesn't follow the octet rule, or the middle hydrogen is not happy. So either you can move this one pair and try a double bond. So now you have N double bond, N single bond O. Still the middle hydrogen is not happy, right? What can you do? We will move one more pair. So we have now double bond oxygen. So this is one structure where everyone is happy, right? And we have used all the electrons. Is there any other possibilities? Can you think of any other possibilities? The way we can arrange the electrons in this structure where everyone has 8 and we are using only 16. You can do a triple bond between the nitrogen and oxygen, right? So the other structure could be so 1, 2, 3, 4, 5, 6 we have used. This guy needs only 2 and this guy will need. Is everyone happy? And we are using only 16. 1, 2, 3, 4. 4 times 8. 10, 11, 12, 13, 14, 15, 16. Oops. 10, 11. What did I say? 9, 10, 11, 12, 13, 14, 15, 16. So these are the 2 possible structures of N2O, correct? So these are the 2 resonance structures of N2O, and how we show resonance structures is by putting a double-headed arrow between them, just to say that the actual molecule is a blend of those 2 structures. Okay, so resonance means it's nothing else. Whenever you have more than one possible Lewis structures, you draw all the possible Lewis structures, put double-headed arrows between them, and that's what is resonance structure mean.
This one has a triple bond between the 2.
That is one more structure you can come up with.
So if you have to draw all of them,
You will put one more. Yes. So
There's
if
no differences between the Lewis structure and resonance structure.
there is no difference, the resonance structure means all the possible Lewis structures, but they are connected with a double-headed arrow. Okay, that is the only difference. So let's see one more activity. That is, there are 3 molecules. Which of the following have resonance? For those that do, how many resonance structures do they have? So which of the following have resonance? So first we have to find out which of the following has resonance. So first thing is starting with the Lewis structure. Start NO3. NO3 has how many electrons? 6 times 3, 18 plus 5, 23 plus 1, the negative charge. So we have total 24, and you have done this molecule in lab. Remember, you could come up with how many structures? Does anyone remember? So this one has actually 3 different structures. Well, let's put the structures. I will do it here. So arrangement is nitrogen in the middle, oxygens on the peripheries, and what was there was a double bond between one oxygen, right? Now what are the other possibilities? The double bond can be between any of those oxygen and hydrogen, right? Sorry, nitrogen. So the second structure is going to be nitrogen. Now I'm going to move the double bond to this oxygen. So rest of them have 6 each, and this guy has only 4. And the third possibility is the leftmost one has the double bond now.
When we did that in the lab, I didn't look at it and say, okay, well that's a different structure. It's the same structure with different bonds.
It's called different Lewis structures.
What does it change? So it doesn't really change anything, does it?
The position of the double bond.
Okay, because I just, for that part of the lab, I was like, I don't really see the significance of.
If you remember in the lab, there were a couple of molecules. One was this, where there was a star, and on the bottom it was written more than one possible structures possible, right? So that's what it means. Technically, chemical reactivity wise, there is no difference between any of those structures. All 3 are nitrate ion. They are all going to react the same way. There is no preference over any of the one structures.
That's the way the pebbles fall, that's all it is.
Yes, but it's just that when you look into the details of the positioning of electrons, there are 3 different positions, or the double bond is moving around.
Technically, what you're saying, the shell could face up or the shell could face down, it's still the same shell.
Exactly.
I just didn't see the significance of it, so I kind of
That's okay, but now you know this.
moved on.
Yeah, that's okay. That's fine. What was Alex's
Does it have
question?
to be double bond?
Yes.
Or could it, does nitrogen have to above it?
Then the oxygen won't be happy. You can use only 24 electrons, right? And this is the only possibility. One double bond between one nitrogen and oxygen. So these are the 3 possibilities. So we draw all the 3 structures and put double-headed arrows between them. Okay, now the second molecule is nitric acid, and there is a clue given here. There is one hydroxyl group. What is a hydroxyl group? Hydroxyl group means hydroxide group, which is an OH group. Okay, so let's try to come up with the structures. So HNO3, which one will go in the middle? Who has the least electronegativity? Of course hydrogen, but hydrogen can never be the central atom, right? Therefore nitrogen is going to be the central atom. So hydroxyl means OH. I'll just put that there. Actually it is an OH minus. So the structure is going to be nitrogen in the middle, and we said there is one OH. That means, well, we have 3 oxygens like this, but the hydrogen is attached to one of the oxygens. That's what it means. That is why it's specific. Otherwise, you might be tempted to put the hydrogen here, right? But to avoid that confusion, that's why it says there is one hydroxyl group. That means the hydrogen is attached to one of the oxygens. So let me put that hydrogen here in this oxygen. So this is our skeleton. Well, we didn't count the number of valence electron. How many we have? 18 plus 5 plus 1, again 24, right? So this also has 24. So we are going to start putting electrons around the peripheral. How many we have used so far? 6 plus 6, 12, 14, 16, 18, 20. We have 4 more to show, right? Well, this oxygen doesn't have any double bond. He already has 2 bonds, right? Now I have all the 24 electrons, but the nitrogen is not happy. What can you do? Look at these 2 oxygens standing with 6 electrons, right? So now you know the possibility. Either you can move this pair here and make a double bond, or you can move this pair here and make a double bond, right? So your possible structures are going to be, what do we get when we do that? You get either a nitrogen double bond O and then a single bond O with the OH group, or the other possibility is the nitrogen with the lower oxygen with a double bond. These are the 2 possible structures. Okay? So, nitric acid has 2 resonance structures, and those are the structures. How about CH4? How many valence electrons? 8. C is in group 4, hydrogen is in group 1, 8. So, our skeleton arrangement is carbon in the middle with 4 hydrogens, and we are using all 8. Is there any other possibility? So there is no resonance in CH4.
Back to the HNO3, why couldn't you double bond the other oxygen that has
This oxygen,
Yeah.
well, this oxygen, again, how should I explain it to you guys?
You would throw an imbalance in the whole picture.
It's not the imbalance. Actually, once the oxygen is made 2 bonds, it needs a lot of energy to force the oxygen to do another bond. So oxygen will usually stay with 2 bonds if possible. So here, this oxygen already made 2 bonds. So when it comes to this molecule, which oxygen you will force for a double bond, definitely these 2 oxygens are the choices. Yes, you will not go consider this oxygen. Okay? Again, we are not doing the energy part or any of those details of bonding, so let's just think it that way. Once the oxygen has 2 bonds, then usually you won't disturb the oxygen. Okay? So, yes, 3, yes, 2, and no. As we have done, we got the structure and the answers. All right. Let's check. It's going to be easy. You know what resonance is.
I hope so. So much fun.
So, oh, what happened? I didn't change the slide. I just started the clock. Isn't that stupid? Stop. I didn't give you the question, right?
Well, that's good. We all got it right. We all got it right.
There is your question. And we will start the clock. So again, go ahead and do the Lewis structures first, and then see is there how many possibilities you have. That's all. That's O3 molecule.
How long do we have?
Well, I'm going to give 2 minutes. You don't need it, but 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So do the Lewis structure, make sure everyone is happy, that is everyone has octet, and then see there is only one structure or more than one. If more than one, how many? Wow, we are almost at the 2 minutes, but only half of the class is answered. Okay, go ahead. No problem, I'll give you more time. Go ahead and finish it and answer. Wow. One more. Does everyone have the clicker? Okay. All right. Let's do the structure. Ozone is, oh, I need the pen back. Okay, so ozone O3. So we have 3 O's, right? How many electrons we have? Valence electrons? 18, because oxygen, group 6, 3 oxygens. So we have 18 electrons. We are showing 4. So we need to show how many more? 14. So you will start with putting 6 around the peripheral oxygens. So you used another 12 and you have 2 more to show, right? So you might put it here. But what's the problem? The middle one is not happy. So what do? We double bond this middle one with one of the peripheral one. So if we are double bonding with one of the peripheral ones, we have to move a pair from the peripheral one, right? So you can move this one here and make O, single bond, double bond O. This guy still has 6. This guy has 2. This guy has 4 now. Everyone happy? All 18 used? One structure. Is there any other possibility? This double bond could be here. Doesn't matter, right? So how many possible structures we have? 3? Where is 3?
Well, because you got a variant of the second one twice.
What do you mean? This is?
You can flip it over and that's another variant.
Yeah, that's one too.
There is only 2. So the other variant is O double bond, O single bond, O 1 2.
I consider that a third variant because it's flipped over even though it's equal.
Where is the third one?
I think he's counting the first one.
Are you counting this as a Lewis structure?
I'm counting that you get either or on the second one that you drew when you have the arrow going both ways.
Yeah, so this is 1, this is 2. 2 structures. Where is the third one?
That one up top.
Oh, that is not a correct Lewis structure. That is not a Lewis structure. Lewis structure means the correct Lewis structure with all the rules balanced, all octet rules, everything followed, right? This was where you are starting. So there is only 2 structures. And I have a combination of answers. I hope people who made the mistake now know what went wrong.
No, what I forgot was the 2 electrons in the middle of.
Ah. So if you don't put those 2 there, then you are showing only 16 electrons, right?
Messes up.
Yeah, it will mess up the structure, that's true. Okay. Now, carbon compounds, again you all know that there is a branch of chemistry called organic chemistry, only to learn about the carbon compounds, but we are not doing any organic chemistry. We will just look into, just very basic where you start the nomenclature, that's all, okay? It's not even we can call it organic chemistry. Because organic chemistry is such a huge, deep branch of chemistry. So carbon is so special among all the elements that this has this particular properties. That is, well, we know that carbon has 4 valence electrons and carbon has the ability to form 4 bonds. But carbon has this special ability that it has the ability to bond to itself. And not just 1 or 2. Long chains and chains of carbons. And we don't see that property with any other elements. Silicon, which is just below carbon, has some of that characteristics. Silicon forms some of these chain compounds, but not very many. But carbon, there are numerous compounds where carbon is bonded to itself like nothing else. Carbon is so happy with itself, it keeps bonding with itself. And most of our body, the biological molecules, they are all made of these long carbon chains and then probably hydrogens and oxygens and some phosphorus, nitrogens. But mostly it's all carbon and hydrogen. And we call it hydrocarbons. So carbon has this particular ability, and there it is showing a couple of molecules where carbon is bonded to itself, and another particular nature is when usually if you try to make elements bond to itself, 1 or 2 is good. More than that, they are not strong. They kind of break apart. But carbon, when it bonds to itself, as long as it can bond, there is no strength issue. All bonds are very strong.
Say that word in the last sentence there.
Carbon molecules are ubiquitous in nature.
What's that mean?
Means abundant
Abundant.
or abundant. Other than that, what can you? I mean, you find it very common or plenty, enough, I mean, and more than enough available. You can think about any of those. So as I said, almost all the biological material is made of hydrocarbons. That is why that sentence is there. So hydrocarbons, as I said, as the name suggests, compounds containing carbon and hydrogen. Hydrocarbon. Now there are 2 major brands of hydrocarbons. One is aliphatic hydrocarbons and the other one is called aromatic hydrocarbon. Now aliphatic hydrocarbons are hydrocarbons where bonds are all localized, single, double and triple bond. What does that mean is aliphatic hydrocarbons, carbons are bonded in a line, like in a straight line pattern or in a chain pattern. And again in aliphatic there are three different types based on what type of bonds carbon forms. If carbon forms only single bonds, then it is called alkanes. If carbon forms at least one double bond, then it is called alkenes. If they have at least one triple bond, then it is called alkynes. So the ending, that's where you, not the ending of three words, anes, enes and ines. Okay? So anes means only single bonds, enes at least one double bond. It can have more than one double bond, no problem, but it should have at least one double bond. And wines means at least one triple bond. Okay? Can have more than one, but at least it should have one triple bond. And aliphatic means the simple word you can remember is chain. When it is in a chain format, it's called aliphatic hydrocarbons. Now the other branch of hydrocarbons is called aromatic hydrocarbons. Why the word comes from the aromatic means most of these hydrocarbons has particular order. Aroma means order, right? That is where the odor or smell. Not order, O-D-O-U-R, odor. Okay. So aroma, remember the word aroma. Aroma means smell, stink, whatever you want. So aromatic comes from that word because most of them have a particular smell which you can recognize. Okay. Now another speciality or the real aromatic hydrocarbons are, they are not chain but they have ring pattern. Not a molecule. The simplest aromatic hydrocarbon, benzene. Look at that molecule. Carbon is like in a ring, right? In a hexagon ring. The next one, naphthalene. There are two rings. So aromatic hydrocarbons, this you can remember, aroma, so they have smell, and their structure wise you can remember they have the ring structure. Okay? So class of hydrocarbons in which carbon atoms are arranged in a 6-atom ring with alternating single and double bonds are called aromatic hydrocarbons.
All our fuels are in rings.
Yes, they are all aromatic hydrocarbons. Well, it's a mix actually. It's not just because the basic fuel propane is an aliphatic hydrocarbon. If you take octane alone, it's an aliphatic hydrocarbon. So when it comes to the vehicle fuel, it's kind of a mix. It's not a pure aromatic or a pure aliphatic.
Not pure.
No, it is a hydrocarbon, but it might be mixed. Okay? Yes. So we are looking at organic chemistry only this much. All you have to remember from this is organic chemistry means study of carbon and carbon compounds. There are many carbon compounds. One of the major classes hydrocarbons, where carbon and hydrogen only hydrocarbons. And among hydrocarbons, two branches, aliphatic, aromatic, aliphatic chain, aromatic ring, and aromatic, that's all. We don't have any more classes, just aromatic ring. But aliphatic, there are three sub-kinds or sub-branches: alkane, alkene, alkyne. Ane means only single bond, ene means one double bond, wine, W-Y-N-E, ine ending means at least one triple bond. That's all you need to remember about organic chemistry. So this table summarizes what we have talked right now. Hydrocarbons, only carbon and hydrogen, again aliphatic and aromatic, and alkanes, alkenes and alkynes based on the bonding of carbon. And aromatic hydrocarbons, everything has ring. So benzene is one ring carbon, and you can substitute the hydrogens with something else. That is when we get more benzene compounds. Don't worry, we are not going to look into any of those compounds. Again, otherwise it's just aromatic hydrocarbons. Now, functional groups. When we say functional group, it is a group or an ion which is introduced or substituted into a hydrocarbon chain. So, when you talk about hydrocarbons, they all contain carbon and hydrogen. So, what is the difference between them? They all should have then the same property, right? So, why do we have these different hydrocarbons? The functional group will give hydrocarbon its characteristic properties. That is, it depends upon how many functional groups you have in a particular hydrocarbon. That tells you what exactly the property of that hydrocarbon is. Now, usually the functional group will have, as I said, a heteroatom. Heteroatom means something other than carbon and hydrogen. Typically, oxygen, sulfur or nitrogen. And sometimes you will find phosphorus also. But oxygen, sulfur and nitrogen are the three most very common heteroatoms you find. Now, an alcohol group, when we say alcohol group, the functional group is a hydroxyl group, an OH minus group. Okay, so this is the picture of, what is this one? That is glucose. Yeah, that's glucose, one of the simplest sugar. If you really look at the, yes, it is the simplest sugar. If you come into organic chemistry, this will be a very simple structure, believe me. So it is one of the very simplest sugars. So glucose, it has, the formula is C6O6H12. So if you count all that, you will find there are 6 carbons, there are 6 oxygens, and there are 12 hydrogens, and this is how they are arranged. Again, don't worry about that structure, it's just showing you as an example. Now this table, it kind of summarizes all the functional groups you will find typically in hydrocarbons. I do not want you guys to worry about this table at all. Okay? It's just for your information. I'm not going to test you on this table. So alcohol, as I said, it's an OH group. So example, methyl alcohol, methanol, ethanol, the simple alcohols. Then ether group is an oxygen. Aldehyde is an COH group. Then ketone, C double bonded O. Carboxylic acid, COOH. Ester, COO. Amine and nitrogen. So don't worry about all this, because when you come to organic chemistry, there is no rules to learn the names. It's just that you really have to work hard and, memorize the structures and names, because there is no pattern like in inorganic chemistry, like what we were doing so far. Naming, we had a lot of rules, right? And you can actually name almost anything if you just remember the rules. But when it comes to organic chemistry, there are no rules. It's really crazy. So I'm not going to ask you to do any of these now, just to show you that table, so you know that there are things like that. Now this is the important part which we will look into. I mean, this is the last part of this chapter we will look into, the important part. The shape of molecules. You had a small introduction in the lab. Remember the words linear, trigonal planar, trigonal pyramidal, tetrahedral, all that stuff, representing the shapes of the molecule. That's what we are going to see now. So shape of the molecule is very important, especially in biology, because shape determines what type of bonding, or bonding in the sense what molecule will interact with what type of molecules, especially the enzyme reactions. You know that in our body there are thousands of enzymes. How do these enzymes exactly know what to do and only at a particular site in our body? How do they know that? It's all based on the molecular shapes. Everything has a particular shape, and there is this mechanism called key and lock mechanism. Just like a particular key will fit into only a particular lock, there are enzymes and molecules with specific shapes, and only particular ones will fit into each other and they can have a reaction. If someone else which doesn't fit into that particular shape, if some other enzyme walks by, Nothing can happen, just like you cannot open the lock with the wrong key. Okay, so you can kind of imagine that way. So shape of the molecules, it's very important. So once again, as I said, the glucose molecule, the structure is given. And on our tongue, when we put sugar in our mouth, why do we feel sweet taste? On our tongue, there are sweet receptors. So sweet receptors means there are, particular cells with a particular shape, and only this glucose molecules, this shape will fit in there. When it fits in there, we feel it's sweet. Now, if a molecule which is responsible for bitter taste, its shape is different. When that comes, that will fit into the particular receptor which will recognize only bitter taste. So if you have that in your mouth, then you will say, oh, the stuff is bitter. Like that. So each receptor has a particular shape, and its corresponding molecule only will fit in there. Okay? So that is the sugar molecule. Now, how do we predict the shape of the molecules? So first thing is again Lewis structure. Lewis structure is the starting point, and the theory called Valence-Shell Electron-Pair Repulsion theory. I know it's a long name, so we call it VSEPR theory. Okay? Because it just takes the first letters of all those words. Valence-Shell Electron-Pair Repulsion theory. So this theory, we are going to look into this theory. This theory explains how different molecules will have different shapes. The basis of this theory is that, well, we were doing all these Lewis structures, and we had so many electrons around the central atom. Remember, all electrons are negatively charged, right? So it doesn't matter whether it is bonding pair or non-bonding pair, they have the inherent nature of repelling each other because they are all negatively charged. And you know that same charges repel each other. Only opposite charges attract each other, right? So when we arrange all these electrons around the central atom, there is some repulsion going on, and this theory is developed based on the electron repulsions. Now, we are going to say that all these electrons, they arrange around the central atom in such a way that they minimize the repulsion and maximize the distance. Okay? Or in other words, you can think there are various molecules. When we do the Lewis structures, we make sure that everyone has 8 electrons around it. But then why we have different shapes? If everyone has 8 electrons, then everyone should have the same shape, right? But that's not the case. We see molecules have different shapes. So why is that? So in each molecule, the electrons will repel and arrange or orient themselves in the space in such a way that they make the distance between them the maximum, so that the repulsion between, distance between them the maximum, so that the repulsion is minimum.
So what you're saying is by having this gap in there allows for a key effect for something else to bond in.
Yes, those shape determines that gap. That gap is actually called the bond angle. How distant are they? That is what the bond angle is. And you know that there are different bond angles, right? With different shapes. So we are going to see what is that. So again, this is how do you apply the VSEPR theory on CH4, one of the very simple molecule. This is what we see. The methane molecule, when you do the Lewis structure, that's what you get, right? And remember, as I said in the lab, when you draw Lewis structure, remember that is only a 2-dimensional picture. So you will think the bond angle is 90 degrees. But in reality, when you make the molecule, you made the molecule, the shape in lab, right? The bond angle is, when you measure, it's actually 109.5 degrees. So these electron pairs are not sitting in a 90-degree angle, right? 109 is more than that. That means they are maximized their distance. So that will give us a 109.5 degree. Again, we are going to look into this theory. This is very important. So from here onwards, everyone, please pay all your attention. Okay? I'm going to do my best to make it simple to you. But this is one of the very important concepts. So when determining the shape, where we start is, as I said, the Lewis structure. And then the second thing is called, first we have to determine what is the parent structure. Parent structure is different from the actual molecular shape. Okay? So we are going from Lewis structure to molecular shape, and parent structure is in between. So how do we decide the parent structure? This is the rule. For each molecule, we are going to count set of electrons around the central atom. On the Lewis structure, okay? Remember that Lewis structure is your basic. First, regardless of anything, as soon as you see the formula, first thing you do is you do the Lewis structure. Then you are going to count the electron sets. Now there are rules for counting electron sets. The rules are, every non-bonding pair is counted as 1. Every single bond is counted as 1. Double bond and triple bond is also counted as 1. Okay? So because multiple bonds, even though they have more than 2 electrons there, they are going to stay together. So we will count that as 1 unit. So let's look at an example. Here is a molecule. Just using, there is no A, B, 3 molecule. It's just A as the central atom, and there are 3 B's around it. We are going to count how many electron sets this central atom has. How many we have? How many we can count? We have 4 sets. Why do we get 4 sets? I'm going to show you. Every pair of non-bonding electrons we will count as 1, 2, 3. A double bond or triple bond is also counted as 1. That means this is the 4th set. So you have, in this molecule, you have 4 sets of electrons.
Where's the 4th one?
The double bond.
Oh.
This is the 4th set. Oops, let me put it out. So that is the 4th set. So this is the first set. It doesn't matter which one you label first. I am just labeling 1, 2, 3, 4 like that. All it matters is you identify all 4 sets around it. Yes?
So all of those pretty much have 4 sets, right?
We are, well, when it comes to the shape, you consider only the central atom. You don't worry about the peripheral atoms. Okay? The central atom determines the shape of the molecule. So make the Lewis structure and you are only going to look at the central atom. Okay? So there are 4 sets of electron in this molecule, in this central atom. Everyone is clear how do we count it? Now, based on the count, we can have 3 possibilities. Some of the molecules when you count, you will find only 2 electron sets. Some of them you will find 3. Some of them you will find 4. Okay? If you have only 2 electron sets, the parent structure is called linear. Only 2 electron sets. If you have 3 electron sets, the parent structure is called trigonal planar. Tri for 3, but trigonal planar.
You have to say the word planar.
Yes. Don't just put trigonal there because there is something else with a trigonal which we will see later. When you have 4 sets of electrons, we will call it tetrahedral. And these are their bond angles. These are fixed. If it is linear parent structure, it is 180 degrees. So those 2 electron pairs, that's what it's showing. 2 electron pairs are 180 degrees apart. If it is trigonal planar, it is 120 degrees apart. If it is tetrahedral, it is 109.5 degrees apart. Now here are those shapes if you want to remember them one more time. Linear shape. Now don't think of these as atoms right now. Okay? Think of these as electron sets. So around the central atom you can have only 2 electron set in here, right? So that is linear shape. Look only at the central atom. Now this central atom has 3 sets of electrons. So this is trigonal planar. This central atom has 4 sets of electrons and that is tetrahedral. Everyone is so far with me? Okay. So these are parent structures, okay? There are more parent structures, but for our class we will look only at these 3 of them. So let's again get it thoroughly. Let's just determine the number of electron sets on each of these and what is going to be the parent structure. So start with the lowest structure. As I said, everything starts with the lowest structure. So NH3, 8 electrons. Okay. So the one goes here, right? Everyone happy? So the central atom is nitrogen. How many electron sets around nitrogen?
4.
Everyone can say 4 sets, because remember each of the bonds we count as 1 and each lone pair is 1, right? There is 1 lone pair, so there are 4. Okay, how about CO2? CO and O. How many electrons we have?
8.
12 plus 4, 16. And remember the structure? This will be the lowest structure. When you draw the carbon dioxide, how many electron sets we have?
2.
Only 2. Remember, double bond or triple bond count only as 1, right? So, and we will consider only the central atom. Do not get carried away with the lone pairs on the outer atoms, okay? Only the central atom. So here carbon has 1, 2. 2 sets of electron. Good. How about SO2? SO2 has 18 electrons. Okay. How will be the shape? Okay, got it. I mean SO2 has Lewis structure, resonance structures, but there is only one structure needed for this purpose. So how many electron sets on SO2? 3 sets. 1, 2, and this is counted as 1, so 3 sets. How about water? O in the middle, H is on the sides. How many sets? 4 sets, right? Okay, now let's come up with the names. So it says how many electron sets and the structure. So ammonia, NH3, we said 4 sets. 4 sets means what is the parent structure? Tetrahedral. 4 tetra. So tetrahedral. When you have CO2, 2 linear. SO2, 3 trigonal planar, and H2O again tetrahedral, right? So these are our parent structures. So everyone knows how to identify the parent structures. Good. Once we have that, we are ready to do the actual shape of the molecule. Okay, so here is our answer. Now, the actual shape of the molecule is not the same as the parent structure. Okay? Or in other words, the actual shape of the molecule will consist only the bonded atoms. The lone pairs, they will not show up in the actual shape. So only the bonded atoms will determine the actual shape of the molecule. So how do you determine the actual shape? First you determine the parent structure, and from the parent structure now just eliminate your lone pairs and then see what do we come up with. That determines the actual structure of the molecule. Don't worry, I'll take you through it. Okay, just get that right now, that actual shape is different than the parent structure. Not all the molecules, some of the molecules. because actual shape is based on only the bonded atoms, not on the lone pairs. Okay? But parent structure, we count the lone pairs also as set of electrons, right? That is the difference. So water molecule, we already just in the previous slide, we said water molecules parent structure is tetrahedral, right? But if you look at the actual shape of water molecules, can you just kind of visualize? Imagine those two lone pairs are not there. What will be the shape? It's kind of a V, a bend shape, right? We are going to see how we get that. So here is the steps, and then I'll take you through the steps using the model. So first step is draw the Lewis structure, then count the number of atoms bonded to the central atom and count the unshared pairs on the central atom, or in other words, count the number of sets of electrons and get the parent structure. Okay? Once you get the parent structure, the step number 4, the molecular shape is derived from the parent structure by considering only the positions occupied by bonded atoms. Or in other words, we will not consider the positions of lone pairs.
So the ones that go in H.
Lone pairs or non-bonding pairs, whatever. We will not consider them for the actual shape. For parent structure, you will consider. So, again we'll start with the parent structure linear. There are only 2 sets of electrons, right? And when 2 sets of electrons are bonded to 2 atoms, there is only one possibility. The structure is linear. Linear is easy because in this, the parent structure and the shape of the molecule is always going to be the same. Because there are only 2 sets. Okay? 2 sets means, of course, it has to be bonded to 2 atoms. So, it is always going to be linear. But when it comes to trigonal planar, when you have 3 sets of electrons, you have the parent structure trigonal planar, and if that's all the 3 are bonding electrons, that is all 3 are bonded to atoms, then the shape is also trigonal planar. But how about among these 3, one set is a lone pair or one set is a non-bonding pair? Now you have to visualize without that one. So I'm taking off that one from the actual shape because this was the lone pair or a pair of non-bonding electrons. Look at the shape now. What is the shape? This is called the bent shape. Okay? So 2 possibilities with trigonal planar parent structure. Either all 3 are bonded to different atoms, then it is trigonal planar shape. But if one is a lone pair, then you will not imagine that in the actual shape. So you are taking it out and the structure is bent. Now when we have, so that is what is shown in the second part. That is when the parent structure, all 3 are bonded, it is trigonal planar. But when one is a non-bonding pair, that is this one, this is a non-bonding pair. Now you have to visualize it without that non-bonding pair. Then the structure is only this, which is the bent structure. Okay, so now let's go to the next one, tetrahedral. Here is your parent structure, tetrahedral. In tetrahedral, when all 4 are bonded atoms like CH4, the shape is also tetrahedral. Now let's imagine one of them is a lone pair. So I'm going to take that one out. See the shape you get. This is trigonal pyramidal. Notice the difference between trigonal planar and trigonal pyramidal. Everyone see the difference? Trigonal planar is symmetrical, right? But trigonal pyramidal, there is a mount. The central atom is, it's not that these 3 are in like this, in 120 degrees, right? These are like kind of downwards and the central atom has a mount, the pyramidal shape. That is why this is called trigonal pyramidal. And we get trigonal pyramidal from the parent structure of tetrahedral by removing one set of electrons. Okay? Now what if in my tetrahedral structure two of them are lone pairs or two of them are non-bonding pairs? So I am removing two. Again, look at the shape once you remove two. Bend. So that's all the molecular shapes we are looking at. There are other shapes like trigonal, bipyramidal, octahedral, all that stuff. We will not go into any of these. These are the simple three molecular shape VSEPR theory which we will look into. Okay? So I'm going to summarize this once again because this is important, guys. You should be, and as it says, trigonal planar and trigonal pyramidal are different. Everyone once again look at the shape and make that picture in your mind. See the difference? Okay. So I'm going to take you through this steps one more time because this is really important. So VSEPR theory, start with Lewis structure. Any molecule, draw the Lewis structure first. Then we have to determine the parent structure. Parent structure is determined by counting electron sets around the central atom. When counting electron sets, we will count every bond, regardless of single bond, double bond, triple bond, all bonds, we will count as 1 sets, and every lone pairs or non-bonded pairs we will count as 1 set. So that will give you the number of parent structure. Okay? So there are 3 different parent structures. If you have only 2 sets, it's linear. If you have only 3 sets, it's trigonal planar. If you have 4 sets, it is tetrahedral. Easy to remember so far? Now this is where your imagination should come. Now linear, easy. Linear means the actual shape of the molecule is also linear because there are no other possibilities. In trigonal planar, 2 shapes are possible. One is all 3 sets are bonding pairs, so trigonal planar itself. Other possibility is one is a lone pair. So you have only 2 bonding pairs and that time the shape is what is it? Bent. Sorry, I started with tri, so sorry. The shape is bent. One unbonded set. So 2 are bonded, one is unbonded. So you have to visualize it without the unbonded one. That is why I took it off. Okay? So you will have to visualize that. You have to put a finger above that thing and then you have to visualize that in your mind because Lewis structure will show you only 2 dimension. It will look like linear but the actual shape is bent. That is why I brought the models. You have to visualize these models. Now when you have 4 electron sets, the parent structure is tetrahedral, 4 tetra, remember that way. When you have 4 sets, it's tetrahedral. There are 3 possibilities. Okay? One is all 4 bonding, so tetrahedral. Or take one out. One is a lone pair, so the shape becomes trigonal pyramidal, not planar. Again, as I said, the difference. Planar is all 3 in the plane. But here, the central atom and the outer atoms are in the same plane. But here it is not in the same plane. Right? The central atom is like on a mount or like a pyramid. So that is where the name comes from. Trigonal pyramidal. Yes?
Trigonal.
Pyramidal. Pyramidal. Pyramid. Egypt, pyramids. Pyramidal. Pyramidal. That's AL. Do you call it oil? Okay. Trigonal, pyramidal, whatever way you want to say it. So again, notice the difference, right? One is everything in the same plane. In here, it's not in the same plane. Now one more possibility from tetrahedral, that is bent, because there are 2 pairs of lone pair. So the actual shape is bent. What? When 3 pairs, it's just nothing. Don't go there. At least remember only this much. Okay? So good. Anyone can predict the shape of molecule from the Lewis structure now? Alright. You need to know that. Now, in hydrocarbons again, look at all those carbons. What is the parent structure?
Which one is first one?
All carbon, I mean any carbon. You can pick up any carbon. Tetrahedral, right? And is there any lone pairs in any of the carbons? No. Carbon can form 4 bonds, and here every carbon is bonded to either 2 hydrogens or 2 other carbons, right? So in hydrocarbons, the aliphatic hydrocarbon or the chain hydrocarbon, you will always find tetrahedral shape with 109.5 degrees. It doesn't matter how long the chain is, as long as it's a hydrocarbon, an aliphatic hydrocarbon with all these single bonds, then it is going to be always tetrahedral and the bond angle is 109.5. Now let us look at aromatic hydrocarbons. Aromatic hydrocarbon, what do you think that shape will be? Look at one of the carbon. What is the parent structure? Just pick up just one carbon. Say for example, let's pick up this carbon. Count the sets of electrons around it. 3 sets, right? Remember, double bond is considered as only 1. So there is 1, 2, 3, 3 sets. If there are 3 sets, what is the parent structure? Trigonal planar. In that there are all the 3 are bonded, right? There are no lone pairs. Therefore, what is going to be your shape? Trigonal planar. So each carbon there is trigonal planar with a bond angle of, what is the bond angle of trigonal planar? 120. Remember the circle, the total is 360, right? So if you divide that exactly 3, it's going to be 120. If you divide that exactly 4, it's 109.5. If you divide it exactly 2, it's 180. That is where the bond angles come from. So all carbons are trigonal planar with 120 bond angles. Now, natural applications of VSEPR theory, as I said, the molecular shapes are very important in living systems, and here is an example how the shape of molecules can, affect things. So, Hem molecule, we all know that we have red blood cells, carry oxygen around our body, correct? And in red blood cells, the molecule called the heme molecules, which is a part of the hemoglobin. Heme molecules are the molecules which carry the red oxygen around the body. Now, a heme molecule, the main structure, it's a big molecule. What we will focus is that structure A. That is the center of a heme molecule, where you can see a yellow ball with 4 blue balls around it. That is an iron, Fe, with 4 nitrogens around it. Okay, that is the heme part of the hemoglobin molecule. Now what happens in reality is, or what happens in our body is, heme molecule will take an O2 and the O2 will attach to the iron and form an FeO double bond O as it shows. O2 is shown in that 2 red balls attached to the yellow one. So it attaches to the iron and forms an FeO double bond O. Because of, it's not showing the lone pairs on that oxygen, but that center oxygen has a lone pair in it, right? If you think about the Lewis structures. So because of this particular lone pair there, it will attach to the heme molecule in an angle, kind of a bend shape, okay? So when it attaches to the heme molecule, there is kind of a V shape forming right here, like here. There is a V shape there, and an amino acid called histidine will exactly fit into that V shape. So in a hem molecule, oxygen comes from one side, histidine comes from one side, and they both like fit exactly into that position. That is what happens. In reality, that is the regular system in our body. But this will work very true for carbon monoxide also. Carbon monoxide, as we know, it is a poisonous gas. And if we get exposed to carbon monoxide also will come and compete for the space with oxygen. And because, well, don't want to go into that details. Let's say carbon monoxide, when it attaches to hem molecule, it is 25,000 times more strongly attaches to hem molecule than oxygen. Or if you have one carbon dioxide molecule and one oxygen molecule, the hem molecule will prefer 25,000 times the carbon monoxide, not the oxygen. Okay? And the carbon monoxide has a linear shape, as you know. So if it comes and attaches, it will attach on a linear way, and it is very lethal. If in that condition, if anyone is exposed to any carbon monoxide, you will die immediately, because it's so poisonous and all the hem molecules are going to pick up the carbon monoxide, not the oxygen. But nature provides some protection to us. Why that histidine group is there? It's to prevent anything else attaching to that site. So this histidine group will kind of push the carbon dioxide to one side. As I said, you can imagine it's like they come in a V shape and attach, okay? Both in a bend shape. So the histidine molecule will come, and now instead of the oxygen, it has the carbon monoxide, but the histidine group will push carbon dioxide to attach in a bent fashion, and in that fashion, it is only 200 times stronger than oxygen, not 25,000. So you have a chance of surviving if you are found immediately and take you to outside where there is a lot of fresh air and oxygen, then you have a chance of surviving. So usually carbon monoxide poisoning, that's what happens. You get exposed to carbon monoxide and the hem molecule will prefer carbon monoxide, not the oxygen. Hey, hem molecule doesn't know. It just prefer whoever is, better shape or better lone pair, whatever the chemistry there. So it will prefer carbon monoxide.
So that histidine is...
The histidine is saving us, yes.
Yeah, but that is only on one side of that molecule?
Yes.
Not both sides?
Not both sides, only on one side. Now the last part, well, this one you have seen in the lab. I don't want to go in very details, but you know that some of the molecules have polarity, right? I mean, we know what is a polar bond is. We have seen that in last class. When there is electronegativity difference, there are polar bonds. And we saw that some molecules are polar and some molecules are non-polar. Well, first of all, if a molecule doesn't have any polar bonds, then by definition it is non-polar, right? But some molecules, they have polar bonds, but overall the molecule is non-polar. How do we decide that? So, well, in polarity lies along the plane of the bond, okay, and non-polar molecule is one that has all non-polar bonds, or the one has all polar bonds cancel out. So how do you decide which one, in which shape the polar bonds will cancel out, in which shape it will not cancel out? Now you can easily understand this because we have seen the molecular shapes. I'm going to summarize it for you. When you have a tetrahedral molecule where all bonds are polar, the molecule is going to be non-polar because it's a symmetrical shape. Whichever way you see, it is the same thing.
Balanced.
Don't say balanced, because balanced comes with a different meaning. It has a symmetrical shape. Remember the word symmetry. So this molecule overall, just like CH4, bonds are polar, but the molecule is non-polar. Now a molecule like BH3, boron and hydrogen. Bonds are going to be polar, but overall the molecule is non-polar because it has a symmetric trigonal planar shape. Whereas something like ammonia, this is not a symmetric shape. Trigonal pyramidal is not a symmetric shape. Therefore, the molecule is going to be polar. Water, bent, it's not a symmetric shape. Therefore, the molecule is going to be polar. So now you can think in this way, as long as you have, after putting the bond polarity, as long as you have 3 of these structures, symmetric structures, your molecule is going to be non-polar. If you have one of these unsymmetric structures, which is bent or trigonal pyramidal, your molecule is going to be polar. This makes it more easier than doing that stuff on the lab book. Okay? Now, only one exception in the tetrahedral is a molecule like CH3Cl, chloroform. Okay? So, I didn't bring a different shape. So,
Really?
maybe I'm stopping. I mean, is it 9:25 yet?
No. Be back.
I don't think so.
9:20.
Okay, yeah, I'll just show you this and we'll stop. So let's say this is our CH3Cl molecule, chloroform. Okay, bonds are polar, carbon is tetrahedral, but is this really symmetrical? No, this is a different molecule, not the same, right? Therefore, this molecule, even though it is tetrahedral, that is going to be a polar molecule. That is one exception, something like that. So now everyone can remember the polarity of the molecules. As long as you have all symmetrical, even though bonds are polar, molecule will be non-polar. And and these 3 symmetrical shapes, non-polar. These 2 unsymmetrical shape, molecules polar. Okay? So remember that much. Alright, so we will have the exam on Tuesday, covering only chapter 7 and 8.